Lecture 13, Scheduling Algorithms. So in the previous topic, and also much earlier in the course, I referenced a very simple scheduling algorithm, which is we just pick whatever is currently most urgent, and that's what we do. In that circumstance, I mean, it's good to be king. If your process, your task, your thread is the one that's currently the highest priority, not blocked one, well, you're up, and you get all the CPU time. Others are maybe not so happy with that, right? That solution has some drawbacks, as you can imagine, and having learned already about things like the scheduling criteria, I think we can already identify the nature of some of the disadvantages. Things like lack of fairness, right, stand out to us, I think, pretty quickly as something that might not be ideal when we choose that as our scheduling algorithm. But that's okay. That's okay. We have lots of options, more than we can possibly talk about in this topic, but for now, we want to talk about the following 10 options. And the 10 options as presented here, and we're going to look at each of them in some more detail. There's more to talk about than just the name. I mean, the names sometimes tell you exactly what they are or what they do, but frequently we need at least a little bit more explanation than the name explains. Or the name might be a little bit misleading. With that said, our 10 options are 1. Highest priority period, 2. First come, first served, 3. Round robin, 4. Shortest process next, 5. Shortest job first, 6. Smallest remaining time, 7. Highest response ratio next, 8. Multi-level queue or feedback, 9. Guaranteed scheduling, and 10. Lottery. And you can see that some of these sound very similar, right? So shortest job and shortest process, next and first, and you can play Mad Libs with it if you want and make up your own. But you can see why we need to explain them in a little bit more detail, and that just sort of taking the name on its own isn't sufficient. So, okay. Now, as input to these algorithms, sometimes we need some statistical information. Sometimes it doesn't matter, but operating systems are likely to collect this information. And the first thing is the time spent waiting to run. So this is how much time has the process been blocked waiting for a resource, whatever it is, whether that's a semaphore, it could be waiting for a disk read, it could be waiting for a network, whatever it is. This is a percentage, well, not the percentage, but the total time that the process has been waiting to run for whatever reason. And similarly, it's also easy to maintain some information about the total time spent executing. So how much CPU time has the process had? Like what percentage of the time has this been running code on the CPU? And then there is the third one, and the third one can't really be measured because it's a predictive element. That is, it is the total time of execution, and there isn't a good way to know that in advance. Desktop operating systems don't ask a user to estimate how long their task is going to run. Supercomputers might. In olden days, batch systems did occasionally ask users to provide an estimate of how long they thought a task was going to take. And what they were asking for was an upper bound. Because if you supplied a number and it was an underestimate and it took longer than said estimate, execution of your program would be halted, and you wouldn't necessarily get the final result because, well, we ran out of time, time's up, please leave. Whereas if you overestimated, the user task might be scheduled with very, very low priority, so you might be waiting an unreasonable amount of time for the data that you were asking for. So I did encourage you to be honest, possibly erring on the side of the expected time being a little bit higher than the actual, but it was hard to know, right? How long do I think it's going to take to run the n-body problem? I don't know. Based on a first run, I can say, oh, well, if it took such an amount of time with this many points, I can maybe make a prediction. But on a first run, it's pretty hard to guess. So it's something that I'm thinking I'm glad we no longer ask people to do. But maybe supercomputers and other batch processing systems still ask for it as a criterion used to sort of assess the priority of the system. Okay, moving on. The one that I call highest priority period, or in German aus dem Weg Geringverdiener. Okay, that's not literally what it means in German. It means, out of the way. Gering is like limited, and Verdiener is earner. So it's basically like a rich jerk saying, out of my way, poor person. This is just saying whichever has the highest priority, we choose it. Okay. Implementing this is not difficult. We could have just one list that's always kept sorted, a heap that's kept sorted by priority, or we have different priority queues, one for each priority level. And if a task is not blocked, it goes in its appropriate priority queue. If priority changes for some reason, manually or otherwise, move it to the correct queue where it belongs. However it's actually stored isn't the important part. It's just whenever we are looking for, as the short-term scheduler, the next task to do, we choose whichever one is the highest priority amongst the ones that are ready. Okay, we know already this is bad, right? This is vulnerable to starvation. A process that is of relatively low priority might never get a chance to run, because there's always something better to do right now. But people manage projects like this, right? That if you used some sort of prioritization methodology for dealing with bugs, it may be the case that certain bugs have been open for years and years and years on end because they're never important enough to be addressed. It's not that the bug isn't real. Like it does exist, and maybe it affects users, but it affects like the one user who has a very unusual setup. And we're not denying that this is a problem. We're just saying there are other things that are more important that need to be addressed before that. And the bug report just sort of sits around forever because no one ever sees it as enough of a priority to do it. That's fine, right? It happens in other situations as well. There are books that I would really like to read. Der Deutsch-Französische Krieg, 1870-71. It's a book about the Franco-Prussian War. Springs to mind, and it's a book I've had on my bookshelf now for something like 7 years, and there's always a different book that somehow I choose over it. As much as I would like to read this because I think it would be interesting, somehow I just don't, right? Why not? Because it's not enough of a priority. So, there's other work to do, there's another book to read, there's a social event, what have you. With that said, in some systems, it is a desirable property to say we just always focus on the thing that is the most important right now. You can imagine this doesn't fulfill all of the short-term scheduling criteria, right? Like it doesn't pay attention to things like response times, and certainly it violates the principle of fairness, but that's okay. It might be suitable for life and safety critical systems where, listen, when something is more important, we don't care about being fair, we care about controlling the robot arm, and other things have to wait. If the robot arm control process is ready, well, out of the way, other things. You want to prevent a situation where, the robot arm goes through the wall and the building falls down and you're dead, right? Fairness is just not as important in this situation as the life and safety critical operations. So choosing the thing that is always at the top of the priority list may be suitable for this situation. Right. Our second is first come, first served. DMV memes notwithstanding, I think people have spent plenty of time waiting at Service Ontario or California DMV and that sort of thing, so I think the pain associated with this doesn't leave you shocked. But it's an obvious algorithm and it's really simple to implement, and that is whichever process requests the CPU first, so whichever one is ready to run, gets the CPU first. And imagine a queue of processes in which all processes are equal. You get in the queue at the back. You advance through the queue one process at a time, and when the process is selected, we always take the one from the front, and we actually just go. If the current process finishes or gets blocked for some reason, the next ready process is selected. Okay. It's not insane. I mean, it's actually a simplification, if you will, of a scheme like, the highest priority period, because it ignores priority altogether, and all processes get a chance to run eventually. Low priority processes don't starve. With an asterisk. Has anybody thought of it? Sure, this presupposes that the process that's currently executing will eventually get blocked or stop running for some reason or another. That's not necessarily the case. You can have a program that has an infinite loop in it, and when you encounter the infinite loop, even though we don't get blocked, it will just keep going on and on and on forever. And that would not be good because, well, then other processes don't get a chance. So it turns out there is a possibility of starvation here. It's rare, but you can't ignore it. You can't pretend that it couldn't happen. So although it does have its advantages, there are some very likely undesirable outcomes in this regard, right? Life is full of first-come, first-served systems, and many of them result in extended periods of waiting. If you call the phone company because they've billed you incorrectly, yet again, you get the displeasure of waiting in line for a very long time to speak to the next available agent who is currently busy assisting other callers. If you don't want to or can't wait so long, your best option may be to try calling again at a less busy time. But first come, first serve is not too difficult to implement, even if it does have potential suboptimal outcomes. And if the average waiting time for a process varies wildly, that's a bit unpleasant from the point of view of a user because it seems kind of unpredictable. Right? Consider if we have three processes, P1, P2, and P3, and let's say that P1 requires 24 units of time to complete, P2 and P3 require 3 units each. Well, if we look above and below, we can see the total time obviously is the same, but the average completion time of these things is very different. Right? If we do P1 first, then the average completion time is 27 units of time, whatever appropriate unit is, whereas in the situation shown below, the total time isn't changed, but the average completion time is less than half. The average completion time is now 13 units of time. And if all of these things are started at the same time and they appear in the they appear randomly, if you will, in the queue, we don't know which one we're going to get. So, yeah. This might make a big difference for the user, right? Seeing processes 2 and 3 completed sooner will probably be viewed positively, but it's also probably undesirable to have this much variation in how long process P2's turnaround time is. You may also note that first come, first serve has a tendency to favor CPU-bound processes. When a CPU-bound process is running, the IO-bound processes wait in the queue just like everyone else, and that might lead to inefficient use of the resources. We've already touched upon the idea that keeping something like disk busy at all times is beneficial, just because it's slow, and maximizing that resource means maximizing our performance. And so if we do this first come, first serve, we may have inefficient use of the resources because I/O devices are suffering idle periods. We're not making the most of the time, the functionality, the units that we have. Right? If a disk write is completed and there's a process that would like to read something from disk, ideally we would like to proceed on that right away. But with first come, first served, that's not really the case. As you can imagine also, with first come, first serve, if we have a cache miss or we need to fetch a page from disk into main memory, okay, we fetch it into main memory, but the process, when it gets unblocked, goes to the back of the queue and has to wait a comparatively long time to get to the front. In a really bad scenario, you could also imagine in that time that the page that was retrieved was replaced during our very long wait time. In which case, it's as if we didn't do it at all, and that's really painful. Okay. So as we can see, I mean, first come, first served is not ideal for all situations, and generally, as it's described, it is non-preemptive. That is to say, a process that gets selected from the front of the queue runs until there is something that triggers a reason to swap to a different process. In theory, one process could, as we've seen with an infinite loop or something like that, it can monopolize the CPU. Whether that's intentional or unintentional is variable, but remember that some people are jerks, and so that wouldn't be good. And one possible solution is to modify first come, first serve to have periodic preemption. And if we do that, we get a new system, round robin. Yes, holy scheduling algorithm, Batman. If you don't know what this is about, you may appreciate the 1960s Batman series, which is incredibly corny and cheesy. If you thought like original Star Trek looked cheesy, let me tell you about 60s Batman. So we've already talked in one context at least about the idea of time slices. And time slices is just a fancy way of saying taking turns, right? Every t units of time, a timer generates an interrupt, and that is the prompt to run the short-term scheduler. And time slicing itself can be combined with many of the strategies that we're talking about today. But when we combine it with first come, first serve specifically, we get round robin. Okay. So the principal issue with time slicing is, well, how big of a slice, right? If I tell you that, I'll give you one slice of pizza, you should probably be concerned more with the geometry of the slice than you should with the count of slices, because you can slice up the pizza basically infinitely. And so, yes, I can give you a microscopic amount of pizza and call it a slice, but you would still go home hungry. Now, so choosing the time slice is clearly key here. And if our time slice is very large, if it's too big, then processes may seem unresponsive. Like you entered a command, you clicked on something, you said to do something, but it's a very long time before your command is acknowledged, before we do something with it. Because other processes are using the CPU, and it takes quite a while before it gets to be your process's turn. And accordingly, short processes might have to wait quite a while. On the other hand, if our time slice t is too small, then, well, our system spends a lot of time handling the clock interrupt and running the scheduling algorithm and not a lot of time actually executing the process. Right? We have too much overhead. The idea of deciding what to do taking up too much time should sound scary, right? Depending on where you've worked on co-op, you may have worked at places that have this problem, that there are too many meetings discussing how we should do the thing, and not enough focus time dedicated to actually doing it. And so, I have been known to say that I would much rather have us fix the second biggest problem, as opposed to spend the same amount of time in meetings deciding how to prioritize the problem so that everybody agrees on what the biggest problem is. Because, yeah, it's likely that we're no closer to actually solving it just by spending all the time discussing what we should be doing. Action is sometimes more important than agreement in this case. But okay, how do we choose T, right? Thoughts? Well, one of the ideas is, study, right? We could look at patterns of the system. And if we see that a typical process runs for, say, R amount of time before getting blocked, it would be logical to choose T such that T is a little bit larger than R. Why that? Well, if T is smaller than R, then processes will frequently be interrupted by the time slicing routine. And so it's just spending extra time on overhead. Processes that are going to use a lot of CPU will definitely need multiple time slices anyway, right? But it's frustrating if the process would take, say, 1.1 time slices because, well, the work of switching that process out and switching it back in may exceed the 0.1 time slice that was left over. So choosing something that's a little bigger than the average will help us by minimizing the number of unnecessary or otherwise necessary switches. If T is larger than R, many processes don't run up against the time limit. They hopefully accomplish a useful chunk of work. And in the ideal scenario, they do a chunk of work, they get blocked on I/O or some other reason, and nobody is unhappy as a result of this. Right? You can't guarantee it. Right? There's no way to know exactly what threads are going to do, and R is an average in this case, and as we should be aware, averages can be kind of misleading, so we don't necessarily get beautifully distributed behavior across all types of thread, but it's a start, right? It's something. Thinking about this even further, round robin does tend to favor CPU-bound processes. I/O-bound processes spend much less time using the CPU because they run for a short time, they get blocked on I/O, and when the I/O is finished, they go back to the beginning, the back of the ready queue. So CPU-bound processes get more of the CPU time. Right? For CPU-bound process, let's say it uses 90% of a time slice on average before it gets blocked, whereas a process that uses 10% of the CPU time before it gets blocked, right? Each of them gets one turn per round, so to speak, but the amount of CPU time in the turn of the CPU-bound process is much larger. So yeah, that might be kind of frustrating to some extent because CPU-bound processes are getting more of the CPU time. To some extent, that's inevitable. If you want more of the thing, you're likely to get more of it. That's a little bit like saying that people who like coffee drink more coffee than people who don't like coffee. And yet, there's fair and there's unfair. So let's modify that a little bit with virtual round robin. And this addresses the unfairness somewhat. It works like round robin, but with this idea that a process that gets unblocked after I/O gets a little bit of priority. Instead of just rejoining the global general queue, we have a special queue where we send the process or the thread that got blocked on I/O when it gets unblocked. Right, and this is called the auxiliary queue, and this is just sort of like an express lane, if you will. Recently, at the time of recording, I spent a bunch of time recording a lecture for ECE 459. There's the mention of it, box checked. That has to do with the impact of priority on queuing theory stuff. But take that course and you can hear all about it. But what we're saying here is that when the scheduler is choosing a process to run, it prioritizes things that are in the auxiliary queue. And if a process runs up against the time limit, so reaches the end of the time slice, then it goes back to the regular ready queue instead. But if it was blocked on I/O, it goes to the I/O queue, it waits there, and returns to the auxiliary queue. And if dispatched from there, it can run for the remaining fraction of its time slice. So if it ran for 22% of a time slice before it got blocked for an I/O, when it returns to the auxiliary queue, when it gets sent to the CPU again, this process that had up till now used only 22% of its time slice could now run for up to 78% of a time slice before it gets blocked. And maybe it gets blocked on I/O again, after another 51%. And so now it's used 73% of its time slice. So when it comes up in the auxiliary queue again, then we'll see another 27% of the time slice remaining. Or maybe on its second or third attempt, it makes it all the way to the end of the time slice, recognizing that it could actually be a very small fraction of time by the time it gets there for real, because it's possible that it got blocked on I/O 2 times and it came back with 5% of a time slice and now it's just running that out. But when that happens, it goes to the back of the regular ready queue. So this diagram shows a bit about the virtual round robin approach, where a process starts out in the general ready queue, it gets dispatched to the processor. If it reaches the end of the time slice, it goes to the back of the ready queue. If it's finished executing entirely, it takes the release transition that's shown there. But if it gets blocked on one or another of the IOs, when it finishes the IO, it goes into the auxiliary queue. And not shown in the diagram, but very important in this regard, is that the auxiliary queue has priority here. That if there's anything in there, we'll take it. If not, then we will look at the regular ready queue. And that is kind of important to note. Shortest process next. Let's go. 20-minute adventure. How hard could it be? Okay, if some information is available about the total length of execution, then we may wish to give priority to short processes. And we touched on that a little bit when I talked about how the old batch systems worked, where you were asked to give an estimate for things. But the goal here is to reduce the average time to completion of a task. Right? The average time to completion is much lower when the shorter processes P2 and P3 run before P1. This does mean there are faster turnaround times and better responsiveness from the point of view of the user. The drawback of this is that longer things have to wait an unpredictable amount of time. How many short processes are there ahead of us? That's hard to know, so our wait time for a longer task is going to be significantly longer. As I've said, this happens in batch processing on mainframes. Programmers are asked to give an estimate. If your estimate is too low, execution is terminated early. If the estimate is too high, then the job might never be scheduled to run or have to wait an unreasonable amount of time. And that your desktop operating system doesn't ask you, like when you start a text editor, how long you think you're going to be. Your boss on a co-op term might not be so accommodating when they ask you for an estimate of tasks. I myself am not super excited about estimates when it comes to tickets. I understand they are sometimes important, but again, I fear a scenario in which too much time is wasted discussing the estimates and trying to nail down exactly precise estimates when it's like, listen, the 2 hours we spent discussing this, we could have fixed the bug. In any case, your boss on co-op might not be so accommodating. You are likely to need to actually give some estimates, and ideally a reasonably reliable one. The kind of thing that we're talking about here, though, is like global, right? How long will the whole process take, or how long will the whole thread be executing? Which might not be the most relevant thing, right? Some things are going to take a very long time, and honestly, we would be better off making a slightly different decision if we had more local information, like what happens right now. So maybe we care about the length of CPU bursts. And that takes us to shortest job first. We'll update in 10 minutes, they said. Yeah, software updates are notoriously hard to have good estimates on, aren't they? So I don't like the name, shortest job first. It's the common name for the scheme. It's what you would look up in a textbook or Wikipedia or whatever. I don't think it's the right name for it, but these things are, as one may imagine, not entirely up to me. This is truly unfair, outrageous. We should call it, if you ask me, shortest next CPU burst. That, I think, is a more descriptive and better name for what it is, but as I say, it's not up to me. And other sciences have trouble with naming things as well. The red panda is not actually a panda, even though you can see where maybe they got the idea, but it's not a panda. Okay, so what we're going to do is choose the process that we think is likely to have the smallest CPU burst. That is to say, the one that we think is likely to use the CPU for the shortest amount of time before getting blocked for something else, I/O or page fault or something to that effect. It's hard to know exactly, right? There's no guarantees in life, and this is one of those situations, but we just are going off of what we think is likely. And if we have two of them that are the same, then we can use first come, first serve to break the tie, or we can choose randomly or something like that. So if we have 4 processes, P1 through P4, whose predicted burst times are 6, 8, 7, and 3 respectively, we would schedule them such that the order is P4, P1, P3, and then P2. Again, this is not a promise that these are the actual CPU burst times, but our prediction is that the average waiting time then is 3 plus 16 plus 9 plus 0. It's the wait time for P1 plus the wait time for P2 plus the wait time for P3 plus the wait time for P4, which is 0 because it goes first. And dividing it by 4 produces the average wait of 7 time units. Time units are, again, whatever you think is sort of reasonable for the scale that we're looking at. Okay, this is significantly better than first come, first serve scheduling. In fact, it is provably optimal in terms of giving the minimum average waiting time for processes. In fact, like moving a short process up means it finishes faster, and that decreases its waiting time. Moving longer processes back increases their waiting time, but the thing that makes this worthwhile is that basically the decreases in waiting time outweigh the increases in waiting time. Right? It's a net benefit, even though that's not necessarily obvious from like how the scheme is devised, but you can show that there is in fact a net benefit to doing this, such that overall the scheme is a net positive, even if something is going to wait a little bit longer. You know, not everyone benefits, but the benefits for the majority outweigh the detriment to the minority. The problem, as you may imagine, is predicting the CPU burst times. As my father would say, the best predictor of future behavior is past behavior. And so on that basis, what we should do is look at past behavior, right? If we gather information about the past, we can take a look and use that to inform an estimate. And so our estimate for the expected CPU burst is based on this formula, and it says S of n plus 1 is equal to 1 over n times the sum from 1 to n of t sub I, where t sub I is the actual recorded burst time for the last time that it ran. Si is the predicted value for the instance, and S1 is a guess at the first value. Right? So what we would actually do, instead of like doing a summation over the last 10 times every single time, is what we would do is just modify the equation every time to update the value, so that when we want to make a guess, we're going to just weight the previous value and add the information from the new one. So if we go back here, right, S1 is going to be a guess at the first value. So at the beginning of time, we have no history information because this process hasn't run yet. That's fine. We need to start with an initial guess of some sort, so we'll pick something, right? Doesn't have to be anything great. We'll just pick something, and then over time we just note down, okay, what was the actual CPU burst, and we make our prediction based on that. And so we will then update our prediction every single time, such that we get a reasonable guess at the next one by giving equal weighting to each of the previous terms. So this strategy is okay, but actually what we should do is probably give more weight to recent values, right? What happened long in the past is maybe not as interesting as what has happened more recently. We've talked on more than one occasion now about the idea that like different processes go through phases, right, where they have different behavior. And a compiler is a good example of this because the compiler, when it's reading and parsing the files, well, that's a lot of I/O, right? It's got to load the files, so wait for them to come in from disk, and it's got to allocate memory for the buffers for them and write the data into the buffers and stuff like that. So there's going to be a lot of necessarily I/O stuff in that phase, but then when it's doing, say, program analysis, then a lot of the stuff is in memory, and we're doing like computationally intensive stuff, CPU intensive stuff, to figure out whatever the compiler needs to figure out. right? So this is potentially misleading if we give each term in the summation equal weight. So maybe what we should do is exponential averaging. And that is, well, giving more recent values a bigger weight in this calculation. And so what we'll do is determine a weighting factor alpha somewhere between 0 and 1 that determines how much weight these observations are given. And so then we just modify the formula so that Sn plus 1 is alpha times Tn, so the last recorded CPU burst time, plus 1 minus alpha times Sn, our previous guess. So that's a pretty simple formula to calculate for the computer. There isn't a need to remember extensive history or anything. We just have to remember what we guessed last time, and we just need to base what we're doing off of that. And for a large value of alpha, then recent observations matter. If we choose alpha equals 1, then we forget about history entirely, and our guess is just, yep, whatever we had last time, that's what we're going to have this time. If we choose alpha of 0, we never update our guess, which is probably bad. We should probably update our guess at some point, but hypothetically, you could just ignore that if you wanted. Okay, so one of the textbook authors, has kindly enough done some analysis on this kind of thing, such that we have some data to go off of here. And the data to go off of here says, well, if we just took a simple average, this is the black line with white boxes, and the observed value is the actual time, so that's the black line with the black boxes. And then the decay factors, alpha 0.5 and 0.8, show up as the green lines. And as you can see, there's not that much difference between them. All considered, they both approximate the behavior pretty well, and it is sort of noteworthy that whatever alpha factor we use, that turns out to be better than the simple average, sort of no matter what we do. And that applies for increasing functions as well as decreasing functions. So I think the graphs make it sort of pretty convincing, if you will, that we should be using the exponential decay factor as opposed to using the simple average. We might incidentally need to give an estimate, say, of S1 equals 0 to start with. It gives new processes the priority, so they get a chance to start, and we get to see what they're actually like. But we'll see, right? Giving them this is sort of like giving them, oh, we trust you, and then we'll see what they actually do. It's reasonable as a first approach. First, we have to give them a chance. Now, there is a chance in such a routine that longer running processes will actually starve. If there's a constant stream of shorter processes, the short ones will continue to get scheduled ahead of the longer ones. So the longer ones just keep getting pushed back over and over and over again, and that's not ideal, right? It's not something that we would feel good about because it's kind of unfair, right? A long waiting process is okay, particularly if it's just long overall. But what we don't want to see is that the process waits an indefinite, arbitrary amount of time, because, well, that would be starvation, and we do not like that. Here's another graph showing our predictions and CPU burst in this case. This a little different from the previous one where it was one direction or the other. Here we are showing, a significant change, right? At some point there is a change in the behavior of the process, and so tau sub I is the prediction, and the actual burst is T sub I. So tau is the blue line, the curvy one, and Ti is the rectangular black one. And this kind of thing is showing that, yes, we will be able to approximate the the new value based on our prediction, recognizing that sometimes there's an abrupt change in the behavior of the process. And then there is shortest remaining time. Almost there. Stay on target. And shortest remaining time is a modification of the preceding strategy, which allows for additional preemption. When a new process is scheduled or an old one becomes blocked, the scheduler will evaluate if it has a shorter predicted running time than the currently executing process. If so, the new or unblocked process will displace the currently executing one and start running right away. So this would potentially allow us to prioritize things that are quick when they show up, right? It arrived, it's ready now, here we go, let's just do it. And that kind of thing is convenient for short-running tasks. It's not always convenient for everybody overall, right? That's the problem. And so, as we can imagine, there is still a chance that long-running processes will starve because there is a constant stream of shorter-running processes, which we don't want. And similarly, if we choose S1 to be 0 for all of the processes, it means when a new process is created, it always preempts the running one. That's okay in some situations. It's not great for everything. We do our best. One interesting advantage of doing something like shortest remaining time is that we no longer need to have time slicing. Instead of interrupting the running process every t units of time, other interrupts like users launching programs, hardware operations completed, and what have you, will be enough to give us the prompts to run the scheduler, generally speaking. The system therefore doesn't have to spend time handling the clock interrupts, which could be convenient, right? There is time that's wasted, or at least used up, going into handling this. And although handling an individual clock interrupt is not particularly expensive, even an inexpensive operation done a billion times is expensive. It does add up, right? It all counts. Now, so far, the scheduling routines that we have looked at are suitable to kind of batch processing systems and not so much interactive desktop systems. So this isn't everything that we would expect to see in, say, a Unix-like operating system. We're going to have to dig a little bit deeper and look at some of the ones that we didn't get to on the list to see what we expect to see on our laptops and phones. Right, at the beginning, I said we were going to discuss some 10 of the scheduling algorithms, and we covered, at this point, 6 of them, ending with the shortest or smallest remaining time. But we still have yet to talk about highest response ratio next, the multi-level queue, guaranteed scheduling, and lottery. But this video has gone on for a bit already, so I'm going to pause it here, and we'll come back in the next topic to consider different and other scheduling algorithms.